Let's start with a problem that sounds small but ends up shaping almost every high-performance CPU ever built. Imagine two instructions. The first writes to register R1. Much later, another instruction also writes to register R1. At first glance, that seems normal. Registers get reused all the time. But now, imagine there is no real data relationship between those two instructions. The second one does not need the value produced by the first. It just happens to use the same architectural register name. And that is where things get interesting, because to the program, both instructions mention R1. But to the hardware, those two values are completely different pieces of data that only share the same label. If the CPU treats them as if they are the same storage location, it creates an unnecessary dependency, a false dependency. And once that happens, independent work gets artificially serialized. Execution slows down, not because the program actually needed it to, but because the machine was trapped by naming. Register renaming is the mechanism CPUs use to break that trap.
The deep, conferring ideas behind modern, out-of-order execution.
Without register renaming, wide superscala issue does not scale properly. Instruction-level parallelism gets choked off far too early, and much of the hardware's potential goes to waste.
So, in this video, we are going to build this idea carefully from the ground up. We will look at why false dependencies exist. We will separate true dependencies from fake ones. We will understand what an architectural register really is and why it is not enough for a high-performance design. We will walk through how the rename stage works, how physical registers are allocated, how mappings are updated, how old mappings are preserved for precise retirement, and how the whole machine stays logically correct while speculatively executing far ahead. And we will connect register renaming to reorder buffers, physical register files, free lists, branch recovery, speculative state, and the basic reason modern CPUs can keep so many instructions in flight at once. If you understand pipeline, superscalar issue, and out-of-order execution, register renaming is the next big idea that makes the whole system click into place. Because this is the point where the CPU stops treating register names as real storage locations and starts treating them as what they really are, programmer-visible identifiers. And once hardware makes that shift, a lot of artificial constraints disappear. So let's begin with the actual problem. At the ISA level, a machine might expose a small set of registers, maybe 16 general-purpose registers, maybe 32, maybe more. Those are the architectural registers. They are the registers defined by the instruction set architecture. They are the ones assembly code refers to. They are the registers the programmer thinks they are using. But the moment you try to build a fast out-of-order core, a problem appears. The architectural register set is far too small and far too rigid to describe all the temporary states that exist inside a speculative machine. Because inside the core, you may have many instructions in flight, all at different stages of execution, many of them writing what looks like the same architectural destination. Consider a simple sequence. Instruction 1 writes R1. Instruction 2 reads R1. Instruction 3 writes R1 again. Instruction 4 reads R1. At the ISA level, that is perfectly normal. But if you look closely, the value of R1 seen by instruction 2 is not the same logical value as the value of R1 produced by instruction 3. Those are different versions of R1. The architectural name stays the same, but the value instance changes over time. And that is the first key idea. A register name in the ISA is not the same thing as a specific physical storage cell inside the processor. It is a logical name whose meaning changes as the program executes. If hardware naively stores all writes to R1 in one actual location, then multiple logically distinct values get forced through the same storage slot. That creates hazards that are not fundamentally about data flow. They are about name reuse. To understand this properly, we need to separate the three classic dependency categories. Read after write, write after read, and write after write. Read after write, often called raw, is a true dependency. If instruction B reads a value produced by instruction A, then B genuinely depends on A. There is no trick that removes that dependency because the data itself flows from A to B. If A has not produced the value yet, B cannot consume it correctly. That is a real edge in the data flow graph. Now look at write after read, or WAR. Suppose instruction A reads R1 and a later instruction B writes R1. Does B really depend on A's data? No. The only issue is that B must not overwrite the register too early before A has taken the old value. That is not a true data dependency from A to B. It is a hazard caused by reusing the same register name. Now consider write after write, or WAB. Instruction A writes R1, then later instruction B also writes R1. Again, the problem is not that B needs A's result. The issue is only that the final visible state must reflect the later write, not the earlier one. That is also not a true data flow dependency between their values. It is another naming conflict. So among these three, only RAW is fundamental. WAR and WAB are false dependencies, or more precisely, name dependencies. They appear because the ISA has a limited register namespace and instructions reuse those names over time. Register renaming exists to eliminate WAR and WAD hazards by giving different logical versions of an architectural register different physical homes. That is the heart of it. But same architectural name, different physical register. No conflict. Let's make this concrete. Suppose you have this sequence. Instruction 1, R1, R2 plus R3, R instruction 2, R4, R1, tree R5, at apply. Instruction 3, R1, R6 minus R7. Instruction 4, R8, R1 plus R99. There are two writes to R1. Instruction 2 depends on the first write to R1. Instruction 4 depends on the second write to R1. Those are two different logical versions of R1. If the CPU only has one internal place corresponding to architectural R1, then the machine has to be extremely careful not to let the second write destroy the first value before instruction 2 has used it. That creates a war-style concern from the perspective of internal scheduling, and the two writers also look WA-related because they target the same architectural destination. But if the CPU renames the first R1 write to, say, physical register P17 and the second R1 write to physical register P23, everything becomes much cleaner. Instruction 2 does not read R1 anymore in the internal representation. It reads P17. Instruction 4 reads P23. Now, there is no confusion. The different value versions have different identities, and suddenly those false dependencies vanish. The machine now sees the actual data flow instead of the misleading register spelling from the ISA. This is a massive conceptual upgrade because once instructions are renamed into physical register, scheduling becomes much more accurate. The core can let the second writer proceed without fear of clobbering the first writer's still needed result because they are no longer sharing the same physical destination. So renaming is not a minor optimization. It is the step where the processor transforms the program from a limited architectural naming system into a richer internal data flow form. Now, before going deeper, we need to distinguish architectural state from speculative internal state. Architectural state is what the ISA promises exists at precise points, especially at retirement and at exceptions. If an interrupt occurs, or a fault is taken, or the program is observed at an instruction boundary, the machine must present a precise architectural view. That means there is a well-defined current value for each architectural register, but inside an out-of-order core, many newer instructions may already have executed speculatively. Some have produced results that are not yet committed architecturally. Some may later be squashed because of a branch misprediction. Some may fault, some may never become architecturally visible. So the core needs a way to hold multiple speculative versions of architectural registers at once without corrupting the committed architectural view. That is another reason renaming matters. Physical registers let the machine store speculative results separately from older committed or still needed values. Each destination write gets a fresh physical register. The rename logic updates the speculative mapping so that future dependent instructions read the new version, but the older mapping is still remembered until the writing instruction retires because the machine might need to roll back. This is where rename maps come in. A rename map, sometimes called a register alias table, tracks which physical register currently represents each architectural register in the speculative machine state. For example, the map might currently say R1 maps to P17, R2 maps to P4, R3 maps to P9. as R4 maps to P12, and so on. When an instruction that writes R1 enters the rename stage, the processor allocates a new physical register, maybe P23, and updates the map so that R1 now maps to P23 for younger instructions. But importantly, the previous mapping, P17, is not instantly discarded. The instruction that wrote the new R1 needs to retire before the old physical register becomes reclaimable. Why? Because older in-flight instructions may still need the old version, and branch recovery or exception recovery may need to restore a prior machine state. So renaming is not just replace name with register. It is a disciplined version management system for register values, and once you see it that way, modern CPU design starts to make more sense. Now let's walk through the rename process more carefully. An instruction enters the front end. It is fetched, decoded, and identified as an operation with source architectural registers and possibly a destination architectural register. At rename, the CPU does two different jobs. For source operands, it looks up the current mapping. For destination operands, it allocates a new physical register and updates the mapping. So suppose the instruction is R5, R1, plant R3. At rename time, the machine consults the current map. Maybe R1 maps to P10. Maybe R3 maps to P14. Those become the instruction source physical registers. Then, because the instruction writes R5, the machine allocates a new physical register, say P27, for the destination. Now the instruction internally becomes something like P27, P10 plus P14. And the map is updated so that architectural R5 now points to P27 for younger instructions. That internal instruction no longer depends on architectural names. The source and destination identities are now explicit physical references. This is powerful because later scheduling logic works with actual producer-consumer relationships in terms of physical registers. When the instruction writing P27 finishes execution, dependent instructions waiting on P27 can wake up. No ambiguity. No confusion with older versions of R5. The physical register identity captures exactly which value is meant. But there is an important subtlety here. When R5 gets remapped from an old physical register, say P8, to the new one, P27, the machine must remember that the old mapping for R5 used to be P8. That old physical register cannot be immediately reused. The reason is precise retirement. If this instruction later retires successfully, then P8 may become free because the new version P27 has now become the architecturally correct state for R5. But before retirement, P8 may still be needed for recovery or for older instructions that have not yet completed. So many implementations store, along with each renaming instruction, the old physical destination mapping it replaced. That way, at retirement, the processor knows which old physical register can finally be returned to the free list. This free list is another key structure. The machine has more physical registers than architectural registers. That extra pool is what makes renaming possible. If the ISA defines 32 integer registers, the processor might have well over 100 physical integer registers internally. Not because the ISA exposes more registers, but because the core needs room to hold many in-flight versions simultaneously. The free list tracks which physical registers are currently unused and available for allocation. When a new destination register is needed during rename, a free physical register is taken from the list. When an old physical register becomes no longer needed, usually at retirement of the instruction that superseded it, it is returned to the list. So the machine is constantly allocating and freeing physical registers as instructions flow through the pipeline. In that sense, the physical register file behaves a bit like a managed storage pool for speculative register versions. Now, one of the easiest ways to misunderstand renaming is to imagine that it somehow removes all dependencies. It does not. It only removes false dependencies. True dependencies remain.
If instruction B genuinely needs the result of instruction A, renaming cannot help.
Suppose R1, R2, plant R3. Well, notch 4, R1, trees R5. After renaming, maybe that becomes
P20, P2, plant P3.
P21, P20, P5. The second instruction still depends on the first. It now depends on P20 specifically. The dependency is even clearer than before. Renaming did not erase it. Renaming made it more precise. That distinction matters a lot. Register renaming is not about cheating the data flow. It is about exposing the real data flow by getting rid of artificial name collisions. This is why renaming is so important for out-of-order execution. An out-of-order scheduler works best when it sees the true dependency graph, not the polluted graph created by limited architectural names. If Reorder and WAU hazards remain, the scheduler gets blocked by relationships that do not reflect actual data movement. Once those are removed, the machine can exploit more instruction-level parallelism. That is where the real performance gain comes from. Now let's connect this to scoreboard-style designs and older machines. In simpler in-order pipelines, register naming conflicts are less painful because the machine largely follows program order anyway. And in some earlier out-of-order approaches, like classic scoreboarding, WAR and WAW hazards were tracked and avoided through control logic rather than eliminated structurally. The machine had to delay certain writes to avoid clobbering values too early. That works to a point, but it becomes much harder to scale as issue width and the number of in-flight instructions grow. Register renaming gives the hardware a cleaner solution. Instead of managing these hazards as constraints, it dissolves them by separating name from storage. That scales much better. And once superscalar issue widths increase, once you want many instructions decoded and dispatched every cycle, once you want a large instruction window, renaming becomes almost unavoidable, because otherwise the machine spends too much effort dealing with fake conflicts. Now let's dig into how sources are handled during rename, because this is where the current mapping really matters. Suppose the machine has already renamed several instructions and the current speculative map says R1 maps to P30, but R2 maps to P11, R3 maps to P7. Now a new instruction arrives, R6, R1 plant R3. The rename stage looks up R1 and R3 in the map. It does not care what those architectural names historically referred to. It only cares what the youngest currently visible speculative definitions are. So it records P30 and P7 as the sources. Then it allocates a new physical register for R6, maybe P41, and updates the map so that R6 now maps to P41. That means any later instruction reading R6 will get P41 as its source. This is how the machine constructs a chain of specific value versions. Each instruction reads the currently visible versions of its inputs and creates a new version for its output. That is basically SSA-like behavior in hardware. Not literally compiler SSA in every detail, but conceptually very similar. Each new definition gets a fresh identity, and each use points to a specific definition. This is one reason many engineers describe register renaming as dynamic SSA generation inside the processor. The architecture may expose a small reusable set of names, but internally the core creates versioned values. Now, if you want an intuition for why this helps scheduling, think about waiting instructions in the issue queue. Each instruction has source operands identified by physical register tags.
Some of those sources may already be ready because the values were produced earlier.
Some may not yet be ready because the producing instructions are still executing. When a producer finishes, it broadcasts or marks its destination physical register as ready. Any waiting instruction that depends on that tag can then wake up. This whole readiness system becomes much more effective with renaming because tags correspond to unique value instances. Without renaming, one architectural register name could refer to different logical values at different times, which would make dependency tracking much messier. Physical register tags give the scheduler exact identities. This is also why rename usually happens before dispatch into the issue structures. The scheduler wants renamed operands, not architectural ones. It wants explicit physical dependencies. Now we should talk about what happens when a branch is mispredicted, because recovery is one of the hardest parts of speculative execution. When the front end predicts a branch and continues fetching down a speculative path, all younger instructions are speculative. They may rename architectural registers, allocate physical registers, and update the rename map. But if the branch later turns out to be wrong, all of that younger speculative work must be discarded. So how does the CPU recover the correct register mapping state? There are a few approaches, but the core idea is that the machine must be able to restore an earlier rename map corresponding to the correct architectural point. Tony's one common strategy is checkpointing. At certain points, especially branches, the processor saves a snapshot of the rename map. If a misprediction occurs, it restores the saved map from the correct branch point and discards the mappings created by wrong path instructions. Those wrong path instructions allocated physical registers are then reclaimed. Another strategy is to reconstruct the map by walking retirement state or some log of prior mappings, though checkpointing is often faster for recovery. The important thing is that speculative renaming can be undone. That is why the machine must distinguish committed architectural state from speculative current state. The rename map you use for current execution is not necessarily the same as the committed map at retirement, and this leads us to another important structure. Some processors maintain both a speculative rename map and a retirement map, sometimes called the committed map. The speculative map reflects the youngest renamed state seen by instructions currently in flight. The committed map reflects the architectural state as of the last retired instruction. When instructions retire in order, the committed map is advanced. If a catastrophic recovery is needed, the machine can restore from the committed map, though finer-grained branch checkpointing is often used for faster mispredict recovery. These details vary by design, but conceptually the processor is always managing versions at two levels: speculative current truth for ongoing execution and committed architectural truth for precise state. Now, let's talk about the reorder buffer, because renaming and retirement are tightly linked. When an instruction that writes a destination register is renamed, it usually gets an entry in the reorder buffer as well. That entry tracks the instruction's place in program order and contains enough metadata to retire it correctly later. One important piece of metadata is the old physical register that the instruction displaced. Suppose R1 used to map to P17. A new instruction writing R1 gets destination P23. The rename map updates R1 to P20. The reorder buffer entry for that instruction remembers that the previous mapping was P17. Later, when the instruction completes execution, its result is ready in P23. But P17 still cannot be freed yet. Only when the instruction reaches the head of the reorder buffer and retires in order does P23 become the architectural version of R1 and P17 become safely reclaimable. This timing is essential. If you free P17 too early, some older instruction or recovery path might still need it. If you commit P23 architecturally too early, precise exceptions break. So retirement is the point where speculative version replacement becomes officially visible. This also explains a phrase people often use: the instruction takes ownership of the architectural register at rename in the speculative sense, but it only becomes architecturally committed at retirement. That is the subtle difference. Rename determines what younger speculative instructions see. Retirement determines what the architecture officially sees. Now, some designs historically used a future file plus retirement register file model, while others used unified physical register files with mappings. There are different implementation styles here, and it is worth understanding at a high level. In one style, there is a large physical register file that holds both speculative and committed values, and the maps determine which physical registers represent the current state. In another style, there may be separate structures for speculative operand access and committed architectural state with copying or handoff at retirement. The implementation details differ, but the logical function remains the same. Multiple versions of architectural registers exist internally, and renaming assigns unique identities to those versions. For understanding the concept, the exact storage partitioning matters less than the invariance. New destinations get fresh version identities. Sources read the currently mapped versions. Old versions remain live until safe to release. Recovery can restore an older mapping point. Retirement makes speculative results architecturally official in program order. If those invariants hold, the renaming system works. Now let's address a natural question. Why not just expose many more architectural registers and avoid the whole problem? It is true that having more architectural registers reduces register pressure and can reduce some name reuse. That is why architectures with larger visible register sets often perform better or are easier for compilers. But even a much larger architectural set does not remove the need for renaming in a speculative out-of-order core. Why? Because the issue is not just that the ISA has too few names. The issue is that the machine has many speculative versions of the same program visible state alive at once.
A single architectural register may be redefined multiple times before earlier instructions retire.
Even if the ISA had hundreds of registers, an aggressive out-of-order machine with deep speculation would still benefit from internal renaming because it needs version storage for in-flight definitions. So more architectural registers can help software and reduce some pressure, but they do not replace dynamic renaming in a modern high-performance core. Another question is whether renaming applies only to integer registers. No. The same idea applies to floating point registers, vector registers, and other register classes, though the details depend on the architecture and implementation. Any place where the ISO presents logical register names and the hardware wants to eliminate false dependencies across redefinitions, renaming can be relevant. Some machines even rename condition codes or flags because status flags can also become a source of false dependencies. If every arithmetic instruction writes a shared flag register, then that shared state can serialize execution unless the machine versions or renames it internally. So renaming is broader than just general-purpose integer registers. It is a general technique for breaking false name-based dependencies in architecturally visible state. Now, let's look at a detailed example from start to finish. Suppose the current rename map is RAW1, say P1, R2, so P2, RA3, P3, R4, the P4, R5, the P5, R6, the P6, and assume free physical registers start at P20 onward. Now, the following instructions arrive in program order. Instruction A,
Instrumentality R2.
Instruction B,
R4, R1, try 5. Instruction C, R1, R6 minus R2. Instruction D, R7, R1 plus R4. At rename, instruction A reads R2 and R3, which currently map to P2 and P3. And it needs a destination for R1, so it allocates P20. Instruction A becomes P20, P2 plus P3 plus P3. The map updates R1 assigned to P20. The old mapping for R1, which was P1, is saved in instruction A's bookkeeping for later retirement. Now instruction B is renamed. Its sources are R1 and R5. But now R1 maps to P20 because instruction A has already updated the speculative map. R5 maps to P5. Destination R4 gets a new physical register, say P21. This instruction B becomes P21, P20, P5. Map updates R4 sir P21. Old R4 mapping P4 is remembered for retirement. Now instruction C arrives. It writes R1 again. Its sources are R6 and R2, which map to P6 and P2. Destination R1 gets a new physical register, say P22. Instruction C becomes P22, P6 minus P22. Map updates R1 P22. 20, old R1 mapping, which is now P20, is remembered in instruction C's metadata. Notice what just happened. With instruction A wrote R1 to P20.
Instruction C also writes R1, but P22.
These are separate physical versions. No WAB conflict internally. And instruction B, which depends on the first version of R1, is already wired to P20. So instruction C cannot accidentally overwrite what B needs. That eliminates the false dependency. Now, instruction D is renamed. Its sources are R1 and R4. At this point, the map says R1 drawn P22 and R4 to P21. So instruction D becomes P23, P22 plus P21, assuming destination R7 gets P23. Now look at the internal data flow. A produces P20, assumes P20 and produces P21.
Tau produces P22 independently of A and B.
D consumes P22 and P21. This is much clearer than the original architectural spelling. The machine can now see that C does not depend on A's result just because both write R1. It only depends on R6 and R2. That means C may execute before B finishes if its operands are ready. And that is exactly the kind of parallelism renaming unlocks. Now let's think about retirement for this sequence.
Suppose it executes and produces P20.
Then B executes and produces P20, executes and produces P22, executes and produces P23. Execution may happen in this order or another order, depending on readiness and scheduler choices. But retirement must still happen in original program order, A, then B, then C, then D. When it retires, its destination P20 becomes the committed version of R1, and the old mapping P1 can be freed. When B retires, P21 becomes the committed version of R4, and old P4 can be freed. When C retires, P22 becomes the committed version of R1, replacing P20 as the architectural state, and then P20 can be freed. Notice that P20 could not be freed at A's retirement if C had not yet retired. Actually, careful here. Once A retires, the prior committed mapping P1 is obsolete, so P1 can be freed. But P20 itself remains the current committed version of R1 until C retires and supersedes it. Only then can P20 be reclaimed. That is an important point. Each physical register stays live until a later committed definition replaces it, and no recovery path requires it. So the lifetime of a physical register is tied to the mapping chain and retirement order, not just execution completion. This is why renaming logic and retirement logic must cooperate very closely. Now let's discuss what happens when the core runs out of free physical registers. This is a real resource limit. Renaming depends on being able to allocate a fresh physical destination for every writing instruction. If the free list is empty or nearly empty, the front end must stall rename until retirement frees more physical registers. This is one of the ways the size of the physical register file influences performance. A larger physical register file allows more in-flight rename definitions and typically supports a larger effective window before rename stalls. But larger structures also cost area, power, and complexity. So physical register count is a real design trade-off. Too few physical registers and the machine chokes on artificial resource pressure, even if execution units are available, are that more physical registers and you sustain deeper speculation and higher parallelism, but at hardware cost. This is one reason aggressive cores tend to have significantly more physical registers than their architectural register sets. Now, let's talk about the rename stage as a throughput bottleneck. In a wide superscalar core, the rename stage may need to process multiple instructions per cycle. That means it may have to perform multiple source map lookups, multiple destination allocations, and multiple map updates in a single cycle. And there is a complication. What if two instructions renamed in the same cycle interact with the same architectural register? For example, suppose in the same rename group, one instruction writes R1 and a younger one reads R1. The younger instruction must see the new mapping created by the older one in that same cycle. This requires intracycle bypassing or dependency handling inside rename. Similarly, if two instructions in the same cycle both write the same architectural register, the younger one must get a new physical register and record that it replaced the older instruction's newly allocated mapping, not the original prior mapping. So wide rename logic is not trivial. It is not just a table lookup. It has to preserve program order relationships, even within a batch of instructions renamed together. As issue width increases, rename becomes a harder critical path problem. This is one reason front-end design in wide or WAR cores is so difficult. The renamer must be both logically correct and extremely fast. Now we should address the difference between value storage and tag tracking, because the term renaming can confuse people into thinking values are literally copied around constantly during rename, but usually they are not. Rename primarily changes identifiers, not data. At rename time, the machine is mostly assigning physical tags. The actual value for a destination physical register is produced later by execution. The source physical registers already identify where the needed values conceptually reside. So register renaming is fundamentally about remapping names and tracking versions, not physically moving register contents during the rename step. That matters because it keeps the concept clean. Renaming is a naming operation. Execution computes values. Write-back marks physical destinations ready. Retirement makes mappings architecturally official and frees obsolete versions. Now, there is a related topic people often mix up with renaming, operand forwarding or bypassing. These are different mechanisms.
Forwarding is about sending produced values directly from one pipeline stage to another consumer without waiting for a full register write round trip.
Renaming is about removing false dependencies by giving different definitions separate identities. A machine can have forwarding without full renaming. A simple in-order pipeline often does. And a renamed out-of-order machine still uses forwarding or broadcast mechanisms to get produced values to waiting consumers efficiently. So do not merge these ideas. They solve different problems. Now let's zoom out and think about how renaming changes the machine's view of the program. At the ISA level, a program is written as a sequence of instructions operating on a fixed architectural register set. That representation is compact and stable for software. but it is not ideal for extracting hardware parallelism. At rename, the machine transforms that sequence into something closer to a dynamic data flow graph. Each destination gets a fresh version tag. Each source is bound to the specific version it needs. This makes dependencies explicit and accurate. So renaming is almost like decoding the hidden data flow structure of the program from the cramped syntax of the ISA. That is why it feels so central once you see it clearly. It is not just a bookkeeping trick. It is the bridge between programmer-facing sequential names and hardware-facing parallel value flow. Now, what about memory? Can we do the same thing with memory addresses? Not as easily. Registers are a small explicit namespace, so renaming them is tractable. Memory is huge, dynamic, and alias-prone. You generally do not know at decode time whether two loads and stores refer to the same address unless address generation and memory disambiguation prove something. That is why register renaming is clean and standard, while memory dependency handling requires separate machinery like load store queues, address checking, speculative disambiguation, and so on. This contrast is useful because it shows why register renaming is such a powerful win. Registers are the easy part of the program state to version cleanly. Memory is much harder. Now let's discuss precise exceptions, because this is one of the biggest architectural reasons retirement exists at all. Suppose an instruction far down the pipeline causes a fault, maybe a divide by zero or page fault. The architecture expects a precise state as if all older instructions completed and no younger instructions did. Renaming helps the core run ahead speculatively, but it does not by itself guarantee precise exceptions. That guarantee comes from in-order retirement. Instructions may execute out of order, produce results into physical registers and update speculative maps, but those results do not become architecturally final until retirement. So if an exception occurs, the core can squash younger instructions and restore a known architectural mapping state. That is the clean separation. Execution can be speculative and out of order. Retirement is precise and in order. Register renaming fits into that by making speculative versions manageable without corrupting committed state. Now let's look at another subtle point. Does renaming always require a reorder buffer? Not in exactly the same implementation form in every design, but some mechanism is needed to track program order, retirement, and recovery. Many mainstream OPM cores use a reorder buffer or functionally equivalent structure. Some alternative implementations distribute metadata differently, but they still need the same logical capabilities. Track instruction order, when results are complete. Retire, in order free old physical registers safely, or recover on mispredicts or exceptions. So when learning the concept, it is reasonable to pair renaming with reorder buffer style retirement, because that is the clearest mental model. Now, one misconception to clear up is this. People sometimes think architectural registers are fake and physical registers are the real ones. That is only half true. Architectural registers are real in the sense that the ISA defines them and software relies on them. They are the contract. But physical registers are the actual storage resources the core uses to implement that contract efficiently. The architectural layer defines meaning. If the physical layer implements it, register renaming is the translation layer between the two. Another misconception is that every physical register always corresponds one-to-one with one architectural register. Not at all. At a given moment, one architectural register maps to one current physical register in the speculative map, but many older physical registers may still exist holding previous versions of that same architectural register. And some physical registers may hold speculative values for instructions that will later be squashed. So the relationship is dynamic and many-to-one across time. That is exactly why renaming works. Now let's talk about why compilers cannot fully solve this problem on their own. A compiler can do static register allocation.
It can assign program variables to architectural registers and try to reduce unnecessary reuse.
It can even target ISAs with larger register files more effectively. But the compiler cannot know the exact dynamic overlap of speculative in-flight instructions inside a particular out-of-order core at runtime. Only the hardware knows which instructions are simultaneously alive, which branches are predicted, which long latency operations are outstanding, and how far speculation has run. Dynamic renaming adapts in real time to the actual machine state. So compiler allocation and hardware renaming are complementary, not competing solutions. The compiler manages the architectural register space across the static program. The hardware manages dynamic versioning of architectural state inside the speculative machine. Now let's consider latency hiding. One of the biggest advantages of out-of-order execution is that while one instruction waits on a cache miss or long arithmetic latency, other independent instructions can continue. But that only works if the scheduler can actually identify independence. False dependencies reduce that opportunity. Suppose a younger instruction writes an architectural register whose older value is still needed by some stall chain elsewhere. Without renaming, that younger instruction might be blocked even though its actual computation is independent. With renaming, it gets its own physical destination and can proceed. That means renaming contributes directly to latency tolerance. It helps the machine find more useful work while older operations are stuck. This is especially important in deep speculative windows. Now, because this is a software execution video, let's connect renaming back to throughput and IPC. A superscalar out-of-order core wants to maximize instructions retired per cycle. To do that, it needs a large pool of ready independent work. The scheduler cannot issue what it cannot see. If false dependencies remain, the visible instruction-level parallelism shrinks. Renaming enlarges the effective window of exploitable independence by removing unnecessary constraints. So higher ICP in modern cores is not just about having more ALUs or wider issue. It is also about correctly representing dependencies. Register renaming is one of the enabling mechanisms that turns potential parallelism into usable parallelism. Now let's go deeper into lifetime management of physical registers, because this is one of the easiest places to become vague. When a physical register is allocated as a destination, it enters the machine as the future holder of a value version. Before execution completes, it may not yet contain valid data. Once execution writes the result, the physical register becomes ready. From that point, dependent instructions can consume it. But even then, the physical register may still be speculative. It is only the current speculative version, not yet guaranteed architectural truth. Later, when the writing instruction retires, that physical register becomes the committed version for its architectural destination. It remains live as long as it is the latest committed version and no newer committed version has replaced it. Eventually, a later instruction writing the same architectural register retires, and at that point, the older committed physical register becomes obsolete and can be freed. So a physical register's lifetime spans allocation, production, speculative use, committed use, and eventual reclamation. That is longer than many beginners first assume. It is not just allocate, write, free.
There is a chain of ownership and visibility involved.
Now, what about instructions that do not write a register? A store, a branch, or some compile-like operation may not allocate a destination physical register in the same way. Rename still matters for their source operands because they need the correct current physical versions of the architectural registers they read. But only instructions that create a register result consume new destination physical register entries. So the pressure on the physical register file depends partly on how many destination-producing instructions are in flight. That affects rename bandwidth and free list turnover. Another question people ask is whether renaming increases latency. In one sense, yes, it adds hardware complexity and another pipeline stage or critical functionality in the front end, but that cost is overwhelmingly worth it in high-performance designs because the gain in parallelism and scheduling freedom is so large. With renaming, you might simplify one stage but cripple the whole back end. Modern aggressive CPUs accept the rename complexity because it unlocks much greater overall throughput. Now let's build an intuition with a non-CPU analogy. Imagine a company where everyone uses the same few project folder names over and over again. Folder A, folder B, folder C. Every time a new version of a document is created, it reuses one of those same visible folder names. If the office literally stored all versions in the same physical folders, people would constantly overwrite each other, wait for old copies to be read first, and create conflicts that are really just naming problems. A better system would keep the user-facing project labels the same, but internally assign each version a unique storage location. Then current project file A is just a mapping to the latest real storage slot, while old versions remain available until nobody needs them anymore. That is basically what register renaming does. Architectural register names are the familiar user labels. Physical registers are the actual version storage slots. The rename map says which slot currently represents each visible register. Once you see it that way, the whole mechanism becomes much more intuitive. Now, there is one more deep point worth making. Register renaming is a statement about abstraction boundaries. The ISA is deliberately simple. It presents a stable programming model, but hardware is free to implement that model in much more elaborate ways as long as the visible behavior remains correct. Renaming is a perfect example. Software believes there is one R1. Hardware may have many physical registers that successively or simultaneously represent different speculative versions of R1. So the machine is not violating the ISA. It is refining the implementation beneath the abstraction. This is a general pattern in computer architecture. Simple architectural contract, complex internal machinery, correct visible behavior, high internal parallelism. Renaming is one of the cleanest illustrations of that principle. Now let's tie this into the rename with problem again with a more concrete example. Suppose the core renames 4 instructions per cycle. Within one cycle, it sees these instructions in order. Instruction 0.
All action R2, R3.
Instruction 1, R4, R1 plant R5. Instruction 2, R1, R6 plant R7. Instruction 3, R8, R1 plant R99. If the rename stage processed them independently without respecting within cycle order, it would get the wrong answer. Instruction 1 must read the version of R1 produced by instruction 0. Instruction 3 must read the version of R1 produced by instruction 2. So rename logic must effectively serialize the logical map updates within the rename group, even if the hardware processes several instructions together.
That requires careful design.
The current mapping seen by each younger instruction is not just the map from the prior cycle. It is the map after applying all older same cycle updates. This is one reason rename logic becomes expensive in very wide designs. You need both speed and precise ordering semantics. Now let's discuss how ready bits and tags interact with physical registers. Each physical register typically has not just storage for a value, but also status tracking. Is the value ready? Which instruction will produce it? Has it been written back? When an instruction is renamed, its source operands are tagged with physical register identifiers. If those sources are already ready, great. If not, the instruction waits in a scheduling structure until the missing tags become ready. Once the producer completes, the destination physical register is marked ready and possibly broadcast to wake dependents. This tag-based wake-up model is tightly tied to renaming. Without unique destination tags, wake-up would be far messier. Again, renaming turns loose architectural names into exact value identities. Now, some architectures support register move elimination or zero latency moves, partly because renaming can help treat some moves as map updates rather than real data movement. For example, a move from one register to another can in some cases be implemented by remapping rather than copying a value through an execution unit. The exact details are microarchitecture specific, but this is a nice bonus of the renaming framework. Once the hardware understands values as tagged versions rather than fixed architectural cells, some apparently real operations become simpler bookkeeping transformations. So renaming does not just remove false dependencies, it also opens up implementation tricks around data movement. Now let's revisit the original phrase in the title, how CPUs remove false dependencies. That is not just marketing language, it is literally what is happening. So false dependencies arise when different logical values are forced to share the same architectural name. Renaming removes that by assigning each new definition a new physical identity. War hazards disappear because a younger write no longer overwrites the old physical register that an older read still needs. Cluster does appear because two writes to the same architectural destination become writes to different physical registers, with retirement deciding which version becomes architecturally final and when older ones can be reclaimed. Only raw remains. And raw is exactly what you want to remain, because that is the real computational dependency structure of the program. This is why a renamed machine is more truthful. It is not inventing parallelism. It is revealing the parallelism that was already there, hidden behind reused names. Now, let's talk briefly about energy and complexity, because renaming is not free, and large physical register files are expensive. Wide rename tables are expensive. Checkpointing maps for branches cost storage and design effort. Wake up and select based on physical tags is expensive. Free list management and recovery logic add complexity. Modern high-performance cores pay that price because the performance payoff is enormous. But it is one reason why simpler low-power designs sometimes choose more modest speculation or different trade-offs. Register renaming is a hallmark of aggressive out-of-order machines because it belongs to that class of techniques where complexity buys substantial performance. Now, can an in-order CPU use renaming? Yes, in principle, some limited forms can be used, and some designs use specialized renaming like tricks. But the major payoff comes in out-of-order execution, where multiple in-flight versions and false hazards would otherwise block scheduling freedom. In a strictly in-order core, the hardware already preserves order strongly, so the pressure to dissolve WAR and WAW dynamically is much less. So when people talk about register renaming, they usually mean it in the context of out-of-order superscalar execution. Now, let's pull everything together with a crisp mental model. Think of each architectural register not as a box, but as a label. That label points to the current physical register version for that architectural state. When an instruction reads an architectural source, it follows the label to the current physical version. When an instruction writes an architectural destination, it does not overwrite the current physical version. Instead, it allocates a fresh physical register, writes the new result there, and updates the label for younger instructions. The old physical version remains alive until retirement and recovery logic say it is safe to destroy. That is register renaming. And once you internalize that model, a huge amount of modern CPU behavior becomes easier to reason about. Out-of-order execution becomes clearer. Reorder buffers make more sense. Speculation becomes more concrete. Branch recovery becomes more understandable. But the difference between architectural illusion and micro-architectural reality becomes much sharper. So when somebody says that a modern CPU has 32 architectural integer registers, do not imagine 32 little hardware boxes doing all the work in a high-performance core. Imagine a visible naming scheme implemented by a much larger hidden pool of physical versions. That is the real picture. And that hidden versioning system is one of the reasons modern processors can execute so many instructions concurrently without violating the sequential architectural contract. That is the elegance of register renaming. It preserves the simple model software expects while giving hardware the freedom it needs. And that freedom is not a small detail. It is one of the key reasons fast CPUs are possible at all. Because once false dependencies are removed, the processor is finally free to chase the real dependency graph of the program. And that is where performance begins. In the next layer of this story, the natural questions become, how does the scheduler use these renamed operands? How do issue queues track readiness? How do reorder buffers manage retirement? And how does the physical register file interact with execution and write-back? But the foundation under all of that is what we covered here. The same architectural name does not mean same physical storage. Different versions need different identities. False dependencies come from names. Register renaming removes them by turning reused architectural names into unique physical register versions. And once the machine does that, the program stops looking like a cramped sequence of overwritten labels and starts looking like what it really is, a graph of values flowing through computation. That is register renaming. That is how CPUs remove false dependencies. And that is why it matters so much in software execution.